In the previous video, we looked at how we can find the expression of the inverse hyperbolic cosine of x. And in this video, we will be looking at the expression of the inverse of the hyperbolic sine of x. And what you will notice is that the method and the idea behind finding the expression is almost identical to the way we determined the inverse hyperbolic cosine of x. First, we write down x is equal to sine of y, which allows us to write that y is equal to the inverse hyperbolic sine of x. And now what we do is we use the fundamental identity when it comes to hyperbolas, which is that cosh of y minus sine of y, and sorry I forgot the squared over here, is equal to 1, which allows us to write that cosh squared of y is equal to 1 plus x squared. Notice that we replaced sine squared of y by x squared because x is equal to sine of y. And therefore, cosh of y is equal to plus or minus the square root of 1 plus x squared. Now I would like to discuss some areas of precaution here, because if we remember the graph of the sine function, we note that in this case, if x equals to sine of y, we can clearly see that the graph of the function goes from negative infinity to infinity, and therefore x belongs to the real number line. And therefore, the domain of the inverse hyperbolic sine of x, its domain goes from negative infinity to plus infinity, and therefore there aren't any issues here. However, cosh of y, if we remember its graph, it goes from 1 to plus infinity, which means that cosh of y always spits out a value that is greater or equal to 1, and therefore it is always positive. And therefore we cannot have a minus sign over here, even though we took the square root. And so this means that cosh of y in this case is the square root of 1 plus x squared, and it cannot be the negative of the square root of 1 plus x squared. Moving on, we use our second identity, sine of y plus cosh of y is equal to e to the y, which means substituting our expressions for sine of y, which is equal to x, and cosh of y, which is equal to square root of 1 plus x squared, we get that x plus square root of 1 plus x squared is equal to e to the y. Now remember, we want an expression for y as a function of x, and therefore we take the logarithm on both sides, which means that y is equal to the natural logarithm of x plus square root of 1 plus x squared. Now once again, we need to make sure that this quantity over here is strictly greater than 0. And the reason for that is because the natural logarithm is not defined for numbers equal to or less than 0. And the way we determine if this expression is greater than 0, well, we already know that if x is greater or equal to 0, this quantity over here will always be strictly positive. But now let's imagine that x is negative. Okay, so we want to know when x plus square root of 1 plus x squared is positive when x is negative. Well, this would mean that square root of 1 plus x squared is greater than negative x, but negative x is a positive number, right? Because since x is a negative number, minus x is positive. Now, we can take the square root of both sides, and since we have two positive numbers, a positive number on each side of the inequality, well, we can take the square root without the square without any problems, and so we have that 1 plus x squared is greater than x squared. And now, canceling the x squares, we get that 1 is greater than 0. But this is also true. This is always true, I mean. And if this is always true, this is also true for x being negative. And therefore, we can clearly understand that x plus square root of 1 plus x squared is always strictly greater than 0. And there we have it. This right here is the expression of the inverse hyperbolic sine of x. And to sum up, we noticed that we used the exact same identities as we did for the inverse cosh of x. And we noticed that there is a logarithm involved, of course, because remember that sine of x is equal to e to the x plus minus e to the minus x over 2. And therefore, we can already guess that the inverse will have logarithms in it. And that is exactly what we have over here.